In this video, we're going to derive the Einstein field equations, which are the main equations of general relativity. They predict the existence of black holes, the expansion of the universe, and gravitational waves. We'll do this derivation by generalizing Poisson's equation for Newtonian gravity to the relativistic Einstein field equations that are agreed on by all reference frames. Let's quickly review what we've learned so far in the last few videos. In Relativity 107a and b, we learned the equivalence principle, which says that local gravitation is equivalent to acceleration, and we showed that gravity is just the curvature of the manifold of spacetime. On large scales, the manifold of spacetime is curved, but in small local regions, it can be approximated by a flat tangent plane. So in small local regions, the laws of general relativity reduce to the laws of special relativity. In Relativity 107c, we learned about the Ricci curvature tensor, which is a 4x4 tensor that measures the curvature of spacetime. In 107d, we learned Newton-Cartan theory, which was Newtonian gravity reformulated using curved spacetime, described by the 0,0 component of the Ricci tensor. And in 107e, we learned about the energy-momentum tensor, which generalizes the mass density to a 4x4 tensor, where the 0,0 component is the energy density, which is basically the mass density multiplied by the speed of light squared. So how do we generalize Poisson's equation to make it relativistic and true in all reference frames? From Newton-Cartan theory, we know that the Laplacian of the gravitational potential is just the 0,0 component of the Ricci tensor. And the mass density is more or less the 0,0 component of the energy-momentum tensor. But this equation alone is not relativistic because the mass density and the 0,0 component of the Ricci tensor are not agreed on by all reference frames due to the effects of time dilation and length contraction. One idea to fix this problem is to simply upgrade the Ricci and energy-momentum components to the full 4x4 tensors, and hope that this gives us a relativistic theory of gravity. This is actually pretty close to the correct answer, however, it's not quite right. Einstein originally published a proposal of setting the Ricci tensor to be proportional to the energy-momentum tensor, but he later realized this was not right and corrected himself in later publications. The problem is related to the divergence of tensors, which is when we take a covariant derivative of a tensor and do a summation with one of the indices. Since the tensors we're dealing with in this video are symmetric, it doesn't actually matter which index we do the summation on. Also, recall that we can raise an index of a tensor by doing a summation with the inverse metric, or lower an index by doing a summation with the ordinary metric. The problem is that the spacetime divergence of the energy-momentum tensor is 0. We learned in Relativity 107e that this is how we express the local conservation of energy-momentum in spacetime. However, the spacetime divergence of the Ricci tensor is non-zero, so there's no way this equation can be correct. However, it turns out that if we make a slight modification and subtract 1/2 times the Ricci scalar times the metric tensor, then the divergence of the left-hand side of this equation is 0. This special combination of the Ricci tensor, Ricci scalar, and metric tensor is called the Einstein tensor, denoted by a capital G. This small modification basically gives us the correct Einstein field equations. However, there's another small modification we can make. Notice that if the derivative of a function is 0, then we can always add a constant to that function, and its derivative will still be 0. Similarly, if the divergence of the Einstein tensor is 0, we can always add a constant to it, and the divergence will still be 0. This constant is called the cosmological constant, denoted by a capital lambda, and it is related to the expansion of the universe. A property called the metric compatibility property says that the covariant derivative of the metric tensor in any direction is 0, so we can also include a metric tensor in our cosmological constant term. Finally, if we take our Einstein field equations and force them to match Poisson's equation in the limiting case of weak gravity and low velocities, we can show that this constant of proportionality kappa is 8 pi times Newton's gravitational constant over the speed of light to the power of 4. So the Einstein field equations basically tell us that mass, energy, and momentum on the right side of the equation directly causes space-time curvature, described on the left side of the equation by the Ricci tensor, Ricci scalar, and metric tensor. This proportionality constant is telling us how much space-time curvature we get for a specific amount of mass, energy, momentum. So this constant sort of measures the stiffness of space-time. This constant ends up being really small, which means it takes a huge amount of mass, energy, or momentum to cause a noticeable amount of space-time curvature. So the rest of this video is basically going to be me proving all of the facts I just stated in detail. First, I'll show how we can get the cosmological constant term from the metric compatibility property. Then I'll prove that the divergence of the Einstein tensor is 0, which is called the contracted Bianchi identity. And finally, I'll derive the constant of proportionality from the limiting case of a weak gravitational field. At the end of the video, I'll talk a bit about the sign conventions for the Einstein field equations, because some textbooks might have plus or minus signs in different places than me, depending on the conventions they use. Let's start by proving that the divergence of the cosmological constant term is 0, which involves the metric compatibility property. Previously, in Relativity 107c, I said that the metric compatibility property of the covariant derivative means that we can take the covariant derivative of a dot product of vectors and apply a kind of product rule, where we get a sum of two terms, one with the covariant derivative applied to the first vector, and the other with the covariant derivative applied to the second vector. This basically means that we keep the angles and lengths of vectors constant during parallel transport along a path. Remember, parallel transporting a vector means that the covariant derivative of that vector along a path is 0. So if we are parallel transporting both v and w, these terms will go to 0. And so the metric compatibility property tells us that the derivative of v dot w along this path is 0. So the angle between the vectors and the vector lengths are constant. If we apply the metric compatibility property to basis vectors, we get this expression. We can rewrite these covariant derivatives of basis vectors using the definition of the connection coefficients. And also note that the covariant derivative of a scalar number from this dot product is just the partial derivative. We can then rewrite all these basis vector dot products as the components of the metric tensor. So this is an alternative way of writing the metric compatibility property. If we bring all the terms to one side, it turns out that all of this equals the covariant derivative of the metric tensor, which equals 0. We sometimes write this statement like this, without a direction in the covariant derivative, since the covariant derivative of the metric is 0 in all directions. So let's prove that this is indeed the covariant derivative of the metric. Recall that, to take the covariant derivative of a vector, we write the vector as a linear combination of basis vectors, then use product rule to take the derivative of the components and the basis vectors. The covariant derivative of the components becomes the partial derivative, since components are just ordinary numbers, and the covariant derivative of basis vectors can be rewritten using the connection coefficients. If we relabel this summation with a mu and factor out the basis vector, we get an expression for the components of the covariant derivative of the vector v. We can take the covariant derivative of the metric in the same way, except we write the metric as a linear combination of two covectors combined using the tensor product. We do this because the metric is a function that takes two vector inputs, and so it's made of a linear combination of two covectors combined together using the tensor product. We use product rule to take the derivative of the components and then the basis, and we use product rule again to get the derivatives of each covector. we can rewrite the covariant derivative of a covector using connection coefficients labeled with omega, which are different than the gamma connection coefficients used for vectors. After relabeling the summation indices to make the basis covector indices match, and factoring them out, we get this expression for the components of the covariant derivative of the metric. We can solve for these omega connection coefficients by defining a covector alpha to be a function that takes the dot product with some vector a. So alpha of v is the same thing as a dot v. So if we take the metric compatibility property and apply it to the case of a dot v, then we can replace some of the a dots with alpha. For the left side of the equation, we can expand alpha in terms of the epsilon basis covectors and expand v in terms of the e basis vectors. Then pull the v components out in front because covectors are linear. Epsilon acting on e gives us a Kronecker delta by definition, and since this is 0 except for when the nu and sigma indices match, we can replace the nus with sigmas in this summation. For the right-hand side of the equation, we can also rewrite the covariant derivative of the covector alpha and the covariant derivative of the vector v in their expanded forms. And since alpha is a covector and linear by definition, we can pull all these coefficients out in front. By definition, the epsilon sigma covector acting on v gives us the sigma-th component of v, and the alpha covector acting on the e sigma basis vector gives us the sigma-th component of alpha. We can then distribute to get this. Now, using product rule on the left side term gives us exactly what we see on the right side of the equation. So these terms cancel with each other. We can then relabel some of the indices here, and we can factor the alpha and v components. Now this formula must be true for any arbitrary choice of covector alpha and vector v, so the only possible conclusion is that the omega coefficients are the negative of the gamma coefficients. So given that we know the omega connection coefficients are just the negative of the gamma connection coefficients, we have proved that the metric compatibility property is the same thing as saying that the covariant derivative of the metric in any direction is 0. And because of this, we can feel free to include the metric times some constant in our Einstein field equations, because we know that this term goes to 0 when we take its divergence, just like the energy momentum tensor. Next, we'll prove the contracted Bianchi identity, which says that the divergence of the Einstein tensor is 0. Remember, the Einstein tensor is defined as the Ricci tensor minus 1/2 times the Ricci scalar times the metric tensor, and we will show its divergence is 0. To make the proof easier to read, I'm going to switch notations and write the covariant derivative direction after a semicolon instead of using the nabla symbol. So the statement we want to prove now looks like this. Before we start the proof, I'm going to quickly review the symmetries of the Riemann tensor. Swapping the third and fourth indices gives us the same component, but with a negative sign in front. Swapping the first and second indices also gives us a negative sign. Swapping the first two and last two indices as pairs gives us the exact same component. And if we cycle the last three indices and add all the components together, we get 0. This last property is called the Bianchi identity. Also recall that summing over the top and lower middle index of the Riemann tensor gives us the Ricci tensor, which is symmetric. And summing over the upper and lower index of the Ricci tensor gives us the Ricci scalar. We're going to start with the first Bianchi identity, which means these three components with lower indices cycled around sum to 0. We'll use this to prove the second Bianchi identity, which is a similar formula, but also involves a covariant derivative index. Finally, we'll use this to prove the contracted Bianchi identity. Proving the second Bianchi identity in general is a bit challenging, so we're going to prove it in the simpler case of local inertial coordinates, where the connection coefficients are 0 at a given point. The second Bianchi identity can be expressed as an abstract tensor equation without reference to any basis or coordinate systems. So if we can prove it to be true in one coordinate system, then it must be true in all coordinate systems. If you want to see the full general coordinate proof of this fact, you can check out my Tensor Calculus 26 video, which is linked in the description. So when we take the covariant derivative of the Riemann tensor, we're really taking the covariant derivative of the Riemann components multiplied by the tensor product of 4 sets of basis vectors. And that gives us 5 terms, one for the component derivative, 1 positive connection term for the basis vector, and 3 negative connection terms for the 3 basis covectors. All of this is equal to the Riemann covariant derivative components. And remember, the Riemann components are given by this ugly formula involving the connection coefficients, which means this formula is very, very complicated. To make life easier, we're going to use a special coordinate system called the Riemann normal coordinates at a point P, also called the local inertial frame. This is an orthonormal coordinate system, so the metric components are equal to the Minkowski metric components. And also, the connection coefficients are all 0. This means that in this coordinate system, all these connection terms go to 0. We can't yet send the other coefficients to 0 because they are derivatives of the connection coefficients, and these could still be non-zero. If we sub the Riemann component formula into here and distribute the alpha derivative, we can use product rule on these terms. And since the result contains connection coefficients without the derivatives, they go to 0. So we have a formula for the Riemann covariant derivative components at our chosen point P in local inertial coordinates. Now I can take these 3 terms from the second Bianchi identity and write them out using this formula. And I'll color code the matching terms. Remember, the order of partial derivatives doesn't matter, so we are free to interchange them if we want. If I sum all these terms together, the blue terms cancel, the red terms cancel, and the green terms cancel. So this proves the second Bianchi identity in local inertial coordinates. And again, since this is a tensor result, it should extend to all coordinate systems. Now let's continue on to proving the contracted Bianchi identity. We'll start with the second Bianchi identity and sum it with 2 inverse metric tensors. If we distribute, this rho mu inverse metric can raise the rho index on these first 2 components. And for now, we'll just let it sit next to the third term. Now, you might wonder if we can raise an index on the covariant derivative of tensor components. And the answer is yes. If we take the covariant derivative of the metric acting on the Riemann tensor, we can use product rule to get a sum of 2 terms. And by metric compatibility, the term with the derivative of the metric is 0. This means that when we have the derivative of an expression with the metric compatibility property lets us slide the metric outside the derivative. So since we can take the covariant derivative after or before applying the metric, we can raise indices after taking covariant derivatives without any problems. Now we can swap the third and fourth indices of these components if we flip the sign to negative, and also flip the first and second indices on these components if we flip the sign to negative. Since we're summing the upper index with the lower middle index, we can rewrite these as Ricci tensor components. We can then use this sigma nu inverse metric to raise all these sigma indices, and then rewrite this summation as a Ricci tensor. Then use this inverse metric to raise its rho index. We can rewrite this summation on this Ricci tensor as the Ricci scalar, and also relabel this new index summation with mu. We can then combine these terms with a -2 coefficient, and then multiply the equation by 1/2. I can also change this lower alpha index to mu if I sum with a Kronecker delta. This is just like multiplying by the identity matrix, and it doesn't change the meaning of the formula. Finally, we can sum with a new alpha inverse metric to raise this alpha index, and use the index cancellation property of the Kronecker delta to relabel this alpha index as mu. We can also swap the inverse metric indices since the inverse metric tensor is symmetric. This statement is actually equivalent to the contracted Bianchi identity. Remember, metric compatibility tells us that the covariant derivative of the metric is 0, so we can just pull it outside of the covariant derivative, and then just apply the covariant derivatives to the Ricci scalar and the Ricci tensor. This proves the contracted Bianchi identity, that the divergence of this term goes to 0. Since this corrected version of the Ricci tensor, called the Einstein tensor, has 0 divergence, we can feel comfortable using it on the other side of an equation using the divergenceless energy-momentum tensor. To complete our derivation of the Einstein field equations, we need to prove that this constant of proportionality kappa is equal to 8 pi times Newton's gravitational constant over the speed of light to the 4th power. We'll do this by assuming the Einstein field equations reduce to Poisson's equation in the limit of low velocity, weak gravity, and assuming the spacetime metric doesn't depend on time. For the low velocity limit, this means that the massive objects which are the source of gravity will travel much slower than the speed of light, so their beta coefficient is basically 0. Their gamma coefficient is basically 1, and there is basically no time dilation. So coordinate time t equals proper time. The 4-velocity vector of massive objects will be dominated by the time component, c, and the other components go to 0. The weak gravity limit means our metric is going to be the Minkowski metric eta, which is a diagonal matrix of +1, -1, -1, -1, plus a small change h, where the size of the components of h are much smaller than 1. To clarify what this weak gravity limit really means, when we're doing summations with a metric, we'll take the h part to be very small. So the metric is basically flat. But when taking metric derivatives, the Minkowski part goes to 0 since it's constant, and only the derivative of the h part matters. Finally, time independence means that in our coordinates, the metric components don't depend on time, so their derivative with respect to time goes to 0. As a consequence, the time derivative of the connection coefficients also goes to 0. We're also going to assume that the cosmological constant term is small enough to be ignored. We're going to assume that basically all gravity is caused by mass, so we'll use a dust-like energy-momentum tensor that describes stationary matter. This is given by the rest mass density ρ times the outer product of two 4-velocity vectors. So basically, the t00 component is ρ times c squared, and all other components are 0. In the weak field limit, we can also lower these indices using the Minkowski metric and show that t00 with lower indices is also equal to ρ c squared. Knowing this, we can find out a lot about what the Ricci tensor and Ricci scalar look like from the Einstein field equations. If we look at the 3x3 spatial components of this equation, we know that the spatial energy-momentum tensor components go to 0, and the spatial part of the Minkowski metric is just a negative 3x3 identity matrix. So this tells us that the 3x3 spatial part of the Ricci tensor is a Kronecker delta, or identity matrix, multiplied by -1/2 times the Ricci scalar. And recall the Ricci scalar is just the trace of the Ricci tensor, which is the Ricci tensor with one of its indices raised using the metric. This gives us R00 minus R11 minus R22 minus R33. As we showed, the diagonal spatial parts of the Ricci tensor are all each equal to -1/2 times the Ricci scalar. So we can combine them to be 3 times -1/2 r. Canceling these minus signs, we get plus 3/2 times r. And solving for R00, we also get -1/2 r. So the full Ricci tensor is just the 4x4 identity matrix times -1/2 r. So in matrix form, our Einstein field equations currently look like this. These spatial components cancel, and we're left with a single one-component equation. The negative Ricci scalar equals kappa rho c squared. And from here, we know that the negative Ricci scalar is also equal to 2 times the component r00. We can use the low velocity limit to solve for the connection coefficients and then solve for r00. Recall from Relativity 107D that we can rewrite the gravitational force equation like this, using the gravitational potential phi. We can force this to match the geodesic equation to solve for some of the connection coefficients. If we use the proper time tau as the path parameter, then these derivatives become the 4 velocity components. Using our low velocity limit, we can replace the proper time tau with the coordinate time t, and only include the time components of u in this summation, which both equal c. If we set the upper index to 0, then this second derivative would go to 0, forcing the 0, 0, 0 connection coefficient to go to 0 as well. So we only include the spatial upper index in this equation. If we force this equation to match our acceleration due to gravity equation, we get that the k00 connection coefficients are the partial derivative of phi divided by c squared. It's worth noting that the other connection coefficients aren't necessarily 0 here, but we don't need to bother solving for them either, so we're just going to ignore them. We can use these connection coefficients to determine the r00 component, which is equal to this summation over the Riemann tensor. We only need to worry about the spatial components in this sum, since the time components go to 0 due to the antisymmetry property of the last 2 indices in the Riemann tensor. Using our formula for the Riemann tensor, these components equal this. And using our time-independent metric condition, the time derivative of this connection coefficient goes to 0. It's also possible to show that in the weak gravity limit, the connection coefficients are very small. So we'll assume that the product of connection coefficients is extremely small and can be neglected. And if we sub these connection coefficients in, we get that the r00 component is the Laplacian of the potential over c squared. So if we sub r00 into our previous formula, we get this. And if we assume Poisson's equation is valid in our limit, we can replace the Laplacian of the potential with 4 pi g rho. We can cancel the rhos and solve for kappa to get 8 pi g over c to the 4th power. This is the constant that's required to make the Einstein field equations reduce to Newtonian gravity in the limit of low velocities and weak gravity. And this completes our derivation of the Einstein field equations. There's an alternative way of writing the Einstein field equations called the trace reversed form. We get this by summing each term with an inverse metric. This will raise the Ricci and energy momentum tensor indices. And when the inverse metric is summed with the ordinary metric, we get the Kronecker delta, because the inverse metric cancels with the ordinary metric after summation. This is just like how we multiply a matrix by its inverse to get the identity matrix. The trace of the Ricci tensor is the Ricci scalar r, and we'll denote the trace of the energy momentum tensor with a capital T. And the trace of the Kronecker deltas is just the number 4, since the trace of the 4x4 identity matrix is just the number 4. Multiplying 1/2 by 4 gives us 2, and solving for r, we get negative 4 lambda minus kappa t. We can now sub this in for the Ricci scalar in our original Einstein field equations. Multiplying out the negative 1/2 and bringing all these terms to the other side, we get this alternate form of the Einstein field equations called the trace reversed form, which looks very similar to the original version, but contains the trace of the energy momentum tensor instead of the trace of the Ricci tensor. It's also possible to solve for kappa using this form of the Einstein field equations if desired. Finally, I'm going to comment on the sign conventions for the Einstein field equations, and the extra minus signs that can pop up depending on the sign convention you use. The Wikipedia article on the Einstein field equations has a helpful guide on the sign conventions that I'm going to refer to. The most obvious sign convention issue is the sign convention for the Minkowski metric, which the Wikipedia article calls the S1 sign. In my videos, I've been using the mostly minus convention, but there's also the mostly plus convention, obtained by multiplying the metric components by -1. Let's take a look at how flipping the sign of the metric will impact the Einstein field equations. The first thing to notice is that if we change the sign of our metric, then we must also change the sign of the inverse metric, so that we can guarantee that the metric summed with the inverse metric gives us an ordinary identity matrix with +1 along the diagonal. Next, we'll notice that the connection coefficients are defined using a summation of the inverse metric with several metric terms. If we flip the sign of the metric terms, then we must also flip the sign of the inverse metric, and this gives us the product of two minus signs in several places in the equation. The product of two minus signs is just a plus sign. It ends up being the case that the formula for the connection coefficients is completely unchanged when we flip the sign of the metric. Since the Riemann tensor is defined completely in terms of the connection coefficients, its sign doesn't change either. And neither will the Ricci tensor, which is just the trace of the Riemann tensor. However, the Ricci scalar involves raising an index of the Ricci tensor, using exactly one metric. So flipping the sign of the metric will flip the sign of the Ricci scalar. However, the Einstein field equation term involving the Ricci scalar also involves the metric. So the metric sign change and the Ricci scalar sign change will cancel each other out, and the overall sign of this term does not change. A similar argument can be made for the term involving the trace of the energy momentum tensor in the trace reversed form. Finally, the cosmological constant term involves exactly one metric tensor, and that's it. So flipping the sign of the metric will change the sign of the cosmological constant term. So after all that, what I'm trying to say is, if we have the Einstein field equations and flip the sign of the metric, the only term in the Einstein field equations that will change sign is the cosmological constant term. So Wikipedia says that the S1 sign is the sign in front of the mostly pluses metric. And in the sign convention I'm showing, the cosmological constant term should have the same sign as the metric. In this video, I'm using the mostly minuses metric, so my S1 sign is negative. This means that my cosmological constant term will also have a negative sign. Now, there are two other important sign conventions to make note of. I've defined the Riemann tensor and Ricci tensor like this. But some authors might flip these terms, effectively changing the sign of the Riemann tensor. They may also define the Ricci tensor using a summation of the upper index and the last lower index. And this also introduces a minus sign, due to the antisymmetry property of the last two indices of the Riemann tensor. I'm going to call the sign in front of the Riemann tensor formula S2, and the sign in front of the Ricci tensor formula SA. So in the Einstein field equations, changing either of these signs will flip the sign of both the Ricci tensor and the Ricci scalar. So I'm going to put S2 times SA in front of both the Ricci tensor and scalar terms. Alternatively, if we remember the definition of the Einstein tensor, we can just put S2 times SA in front of the Einstein tensor. So we have our three sign conventions, S1, S2, and SA. And this is how they affect the signs in the Einstein field equations. In this video, I use minus for S1 and plus for S2 and SA, so my field equations look like this. This paper by Einstein actually uses a different sign convention than me, so you can see there's an extra minus sign here that I don't have. You'll notice my sign notation is slightly different from Wikipedia's notation, which uses S3 instead of SA. What I call SA, Wikipedia calls S2 times S3. The Wikipedia convention ignores the cosmological constant term here, so in my opinion, their sign convention notation is incomplete. I'm pretty sure the cosmological constant term would get an S1 times S3 sign to make things consistent. So to sum up this video, we started with Poisson's equation for Newtonian gravity, which is not compatible with special or general relativity because the mass density can change for each observer due to the effects of length contraction. We upgraded the mass density to the relativistically invariant energy-momentum tensor, and upgraded the Laplacian of the potential to the relativistically invariant Ricci tensor. This was close to the correct equation, but it wasn't quite correct, because the right side of the equation has zero divergence, and the left side of the equation has non-zero divergence. We used the contracted Bianchi identity to prove that this modified version of the Ricci tensor, called the Einstein tensor G, has zero divergence, which makes it a suitable left-hand side of our field equations. Also, the metric compatibility property tells us that the covariant derivative of the metric tensor in any direction is zero, so we can also include a term with the metric in our equation, where this constant lambda is called the cosmological constant. We finally showed that this constant kappa must be 8 pi g over c to the 4, if we want the equation to match Poisson's equation in the limit of low velocities and weak gravity. Now that we've derived the Einstein field equations, in the next few sets of videos, we will use them to understand gravitational waves, black holes, gravitational time dilation, and the expansion of the universe, as well as other effects predicted by general relativity.